everyone, this is a quick video on Stein's lemma. This particular lemma came up for me the last couple times this week, so I thought it'd be really helpful just to do a video to keep it on the top of my mind. So for Stein's lemma, if we have x, which is normal mu sigma squared, and some differentiable function g, such that where the expected value of the derivative of g of x is finite and exists, then the expected value of g of x, x minus theta, is equal to sigma squared expected value of the derivative of g of x. So this is what we are trying to prove. So for our proof, let's switch colors for the proof. We have expected value g of x, x minus mu. So I used a theta up here. I should have used a mu, so I don't change that on you. Mu is equal to 1 over square root of 2 pi times sigma integral negative infinity to infinity g of x, x minus mu, exp to the negative x minus mu squared over 2 sigma squared dx. And to evaluate this, we're going to use integration by parts, where we have an integral from u, derivative of v is equal to u v evaluated at the integral bounds, minus the integral from derivative of u times v. For this particular formula, we're going to have u equal to g of x. So the derivative of u is just equal to the derivative of g of x. V, or the derivative of v, is going to be equal to the rest, which is x minus mu, exp minus x, or e to the power of negative x minus mu squared over 2 sigma squared. The antiderivative of v is equal to negative sigma squared exp negative x minus mu squared over 2 sigma squared. So this means that the expected value, g of x, x minus mu, is equal to 1 over the square root of 2 pi sigma g minus x, the sigma squared, negative sigma squared, and put that negative up in front, exp minus x minus mu squared over 2 sigma squared. And this is evaluated from negative infinity to infinity, minus 1 over square root of 2 pi sigma squared integral g of x times negative sigma squared exp, or e to the power of negative x minus mu squared over 2 sigma squared dx. Now this first term actually goes to 0, not infinity, goes to 0, because we have this infinity, and to the e to the negative infinity ends up being e to the negative infinity ends up being 0. Then we have same thing, this negative infinity gets plugged in, negative infinity squared becomes negative infinity. Negative infinity squared times a negative is still negative infinity, so this whole term goes to 0. We see that there's 2 negative signs in the second term, so that means we have a positive value. I'm going to rearrange this a little bit so those negative signs cancel out. I'm going to pull this sigma square out in front, so sigma squared, and then I'm going to have that integral, which should be from negative infinity to infinity, And I have g, the derivative of g of x, over square root of 2 pi sigma squared, e to the power of negative x minus mu squared over 2 sigma squared. Now, this is just the regular expectation of the derivative of g of x. So we can use the law of the unconscious statistician and just go expected value of g, derivative of g of x. And so that proves the lemma. That's all we have to do.